Alright, welcome to Light, Part 2. First part we looked at what produces light, some different wave properties that go along with it. In the second part we're going to go through, now that we know that light is an electromagnetic wave, we're going to look at the electromagnetic spectrum, all the different examples and forms of that electromagnetic wave. So we'll start off with an overall picture of the electromagnetic spectrum. You probably want to pause the video here, make sure you get all this copied down, kind of sketch it out, make sure you pay attention to the fact that the left side of the picture has a higher energy and the higher frequencies, and the right side has the lower energy and the higher wavelengths. So you can see that in the drawings, and you can see it with the words there as well. Right in here where I have the rainbow drawn is the visible light, and the UV is the ultraviolet. So we'll go through this section by section and look at some different examples of each. So we'll start with radio waves. Those are pretty obvious in terms of the main function we're probably familiar with. A typical radio in our car picks up the radio station, the radio signals that come from the radio station, also TV signals that you might get over the air, not through cable or satellite specifically, travel in the radio waves section. These are very long waves and have very, very low frequencies typically compared to other electromagnetic waves. They also have the lowest amount of energy. After the radio waves, we have microwaves. It's not just the oven that you have in your house. The microwaves are what are used in the oven to cook the food. Also your cell phones send their signals to and from the different cell towers and so forth between phones with microwaves. The microwave oven itself basically just has a microwave generator, sends a bunch of microwaves into the metal box that is sealed, and what it does is it causes the water molecules in the food or anything, cause those water molecules to resonate. They have a similar frequency to the resonant frequency of those water molecules. So as they vibrate, it makes, just like rubbing your hands together, it gets warmer, which heats the food from the inside. Microwaves are not typically a danger to us. They do not have enough energy to cause cancer, to cause any mutations to cells. There's also another example we'll come back to here in a minute. This is a microwave gun that the military has developed using microwaves. We'll look at that as well. Next we have infrared radiation, or infrared rays, or infrared waves. This is what you sense as heat. When you walk outside in the sunlight, the first thing you feel from the sun would be the actual infrared. Eventually you'll feel the air warmed up or you touch something else, but the infrared waves themselves is what we feel as heat. If you open up a normal oven that you have in your kitchen, when it's on, it has the red heating coils in it, or electric heater of that nature, you'll feel that infrared radiation. Also, a lot of remote controls use infrared radiation. If you have a little bulb on the end of the remote control, it's using mostly infrared radiation to send signals to the devices you're controlling. Infrared waves, you can see the colors in these pictures. These are artificially colored with the infrared cameras, but it takes the different frequencies and translates it into colors that we can see. And there's always going to be a scale associated with it. So over here you see the 95 degrees Fahrenheit in the bright yellow, and then down here around 76 is in the blues. With that, typically reds are warmer, like the horse here. Blues and greens are cooler. You can see this on this house here. There's a lot of heat at the top, so it's losing a lot of energy through the top here and through the windows in this case. I mentioned remote controls. Here's a little clip of an old remote control that we had in my old classroom. That when you press the buttons, it lights up. Now you can't see this in person. The camera that I had at the time would pick up infrared radiation, and some cell phone cameras will still do that. You can take your remote control and video the light while you're pushing the buttons, and you'll be able to see that possibly. It just depends on the camera itself. Also, you may have noticed that the lights were blinking on here at different rates when I pushed different buttons, and that's how the object itself or the device is able to tell what it's supposed to do. So it's basically sending different patterns of that light signal to the device. I skipped the microwave gun earlier. We were talking about microwaves because part of the process of this gun uses infrared radiation as well. So now that we have both microwaves and infrared radiation that we've looked at, we can look at how this device works.
These service personnel, playing the role of an unruly mob at Georgia's Moody Air Force Base, are about to fall prey to an invisible ray. The hulking panel atop this Humvee is part of what the U.S. military calls the Active Denial System, or ADS. It's designed to incapacitate enemy combatants with an unnerving, non-lethal sensation of intense heat. Watch as the ray silently strikes and scatters the crowd.
The active denial system has three great characteristics. First of all, it's safe. Second, it's effective. And third, it has a tremendous range compared to the other non-lethal weapons that today's warfighter has.
This is the heart of this 100 kilowatt transmitter. This is the gyrotron. 200 kilowatts of electricity is fed in, and 100 kilowatts of radio frequency comes out. That millimeter wave energy comes out an aperture underneath the main reflector, hits the subreflector, which illuminates that main reflector and sends a roughly antenna-sized beam downrange. Those holes that you see in the antenna are for the cameras and other visual equipment that the operator uses so that he knows exactly where that beam is going.
It's operated by a joystick. The operator looks into the console, sees exactly what that antenna is aimed at, moves the joystick left, antenna slews to the left, same way to the right. Then when there's an individual who's identified as a troublemaker, he has a cursor. He can put that cursor on that individual, pull the trigger that's on the joystick, and the energy is sent downrange at the speed of light.
The electromagnetic radiation released by the active denial system is similar to the microwaves in your microwave oven, in that it causes the water molecules in the target to become excited and heat up. But that's where the similarity ends. The ADS is designed to heat only the very surface of the skin. It does this by outputting only the carefully chosen radio wave frequency of 95 gigahertz. Even though it can easily penetrate clothing, the ADS generates a much shorter and safer wavelength of radio waves than those used in microwave ovens.
The active denial system millimeter wave directed energy beam reaches 1/64th of an inch into human skin. So that is the most outermost layer of the skin, roughly equivalent to about 3 sheets of notebook paper. It is essentially affecting the pain nerves in the outermost layer of the skin, heating them up and causing an immediate repel.
Alright, so here's a part I really want you to see, and this is where the infrared comes in. These are infrared cameras down here that are viewing the same thing that's up here at the top. So if we move back just a little bit here, you can watch it again, and you can see the people moving here and here, and when that gun is turned on, they heat up instantly, which makes it very warm.
Aware of what's about to happen,
Engage.
can't help but flinch when they feel the heat.
This is the first time I've experienced the beam from the active denial system, and it feels like an intense warmth feeling, kind of similar to opening a very hot oven door, and it's a compelling feeling that you want to get out of the way of this beam. If you were not expecting this, it would definitely shock you and make you want to move.
Next up, visible light. This is what's detected by human eyes. This is what we see. Here's the basic spectrum, and commonly referred to as Roy G. Biv. If you start on this side over here, Roy G. Biv. I have it drawn this way to match the original picture that we have at the very beginning of this video and everything. So it shows you the general range of the wavelengths of the visible light that we're dealing with. So around 400 to 700 nanometers is the range that humans can see. It's a tiny, tiny piece of the full spectrum. We'll look a little bit about how we see things. So here's a basic diagram of your eye, and the light will come in from the left here, goes in through the cornea, which does most of the focusing. And then you have the lens, and then you have the vitreous humor in the middle. There's a thick gel, and then it hits the retina on the back of the eye there. And you have different light rays coming in, and they'll all get focused. And that's how you get an image back there, like a projector projecting something up on a wall or a screen as you look at it. The retina is composed of some nerve cells, referred to as rods and cones because of their physical shape under a microscope. The rods respond to the intensity of light, the brightness. This is what makes you close your eyes when you see a bright light and look towards the sun. It's what makes it hurt when you walk out into the bright light, maybe after watching a movie on a summer afternoon. Cause you to close those eyes really fast so the light doesn't damage your eye itself. The cones respond to the frequency of light, which we refer to as colors in the visible part of the spectrum. When we see something that is blue, it's related to a particular frequency. And so red, green, and blue are the three types of cones that we typically have on our retinas that are stimulated by those particular frequencies of visible light. And then the mixtures of those three colors and frequency gives us all the colors that we're able to perceive. Here's a little clip here. Take some projectors, little spotlights of these three colors, and kind of line them up, overlap them, mix them together, and you see we get white light is made up of all the colors. Specifically, it's just red, green, and blue in equal amounts. And there are overlaps between the blue and the green, the red and the green, and the blue and the red. And this gives us our basic chart of primary colors of light, red, green, and blue, and our secondary colors of light, cyan, magenta, and yellow. You'll notice in here that yellow and blue, where they overlap, actually give us white. All right? Red and cyan overlap to give us white, and magenta and green overlap to give us white. So these are what are known as complementary colors, or opposite colors. So anything that mixes together in terms of light to give you white would be an opposite or complementary color. Now the other types of colors that you're familiar with would be paints, crayons, art colors, things that we call pigments. And so what were the secondary colors of light are the primary colors of pigments. We have magenta, yellow, and cyan. All together mixed equally would give us black. And then we have our secondary colors of pigment. Cyan and magenta give me blue, magenta and yellow give me red, and yellow and cyan give me green here. You may notice in this picture as you look at it that yellow and blue do not make green. Yellow and blue mix together and make black. All right? If you want to get green with pigments, you have to have yellow and cyan. That's what gives you the green there. Now typically most of the blues that we run across in our colors are not a pure blue. They have a little bit of green in them. They're somewhat a cyan, and so that's where the green comes from. Because I'm not arguing with the fact that you probably used a yellow crayon and a blue crayon, or yellow and blue paint, and gotten some green to it. But you're not going to get that if the colors are pure blue and then the pure yellow that you're dealing with there. You might notice that these three colors are what you have in the color cartridges in your ink printers and color printers. You probably have another cartridge that's black separate from that because it's real expensive to try to make a really pure yellow, cyan, and magenta to give you a pure black, so they make a separate black ink to do that. One of the things that we can look at as well with this is kind of what we see. White light, we said, is the red, the green, and the blue that shines down on a blue object, and we see the color blue. All right, so the red, the green, and the blue all hit that blue, but only the blue gets reflected. The red and the green get absorbed. So again, light is the only thing that you see. So if you see something blue, it's because you see the blue light reflecting off that object or coming from the source. Same thing with the red object over here. All these three colors would hit it, but only the red gets reflected specifically. So if we had that same blue object, but we only shine red light onto it, the red light gets absorbed. So if we were to look at that blue object under just red light, it would look black. Right? Black is the absence of light specifically. So here's some examples of that. You have white light shining on a couple of different objects here. Put red light on it. The red writing that was on the card seems to disappear because the card itself is reflecting only red light. So where it was white, it reflects the red, and where it's red, it reflects the red, and it all blends together. You notice these are a little bit darker because there's not as much red reflecting off of them as the other colors total over here. But you notice here in this picture, the green shining on the red hearts and the blue shining on the red hearts, they look black because there is no red to reflect off of them. The reason this looks red over here is because red is reflecting off of them from the white light as you look at it. So things can look different under different types of lighting. You might have noticed that where you see something that looks a particular color in a store and you take it outside in the sunlight and it looks a slightly different color. Maybe take it home in the lighting in your house and it looks even different than that. It just has to do with what colors are actually present in the light that you're using. Last thing I want to share with you about how you see things is what we call afterimages. And so as we go through these next few slides and everything, I may not let it sit there as long as you might need to look at it, so you might need to pause to see some of the effects. Some of you may not see it very well at all. If you don't, then just listen to what I have to say about what you should be saying and why it works that way. So with this particular image here of this light bulb, it's all black with the wire filament in here being white. So if you stare right about here for about 5 to 10 seconds, after about 5 seconds, most people start seeing a little glowing around the bulb itself. And then if we go to at least about 10 seconds or so staring at that filament, if I flip to a blank white screen, you should see kind of almost a floating whitish light bulb on the white background there. And so what's happened is you're getting an afterimage here. Your eyes were sending signals from all the white areas on the screen to make all of your rods and cones fire off and send a signal to your brain saying that they were seeing this light, receiving this information, but the black area was not. And so those particular nerve cells weren't responding to any stimulation. And then we all of a sudden switch over to the blank screen where the entire screen is full of white. All the nerve cells are responding to that white light, and the ones that were black and not working before are more noticed by your brain and gives you that afterimage effect there. So the next few things will kind of give you examples of that. With this one, you can either stare at the X here on the buttons, or you can stare at the center of his nose right here. This is what I call a mud man, because it's definitely not a snowman unless you're making snow out of black snow. So if we just stare at this, and then I'll switch it to the white screen, and you should be able to see an outline of a snowman and be able to see the actual buttons and the circles for his eyes and nose and everything. Again, you can go back and look at that yourself if you'd like to. Again, sometimes it helps to blink a little bit to see the afterimage, and it'll fade away a little bit as you go. In this case, we have colors afterimages that we'll be able to see. So over here you have the red cones in your eyes and your retina are being stimulated here, and you have the cyan, which is blue and green, nerve cells are being stimulated here. And if you stare right about here in the middle, you don't need to look at both of them independently, but just look in the middle of them. Again, let it sit there for about 10 seconds or so. You probably see some glowing around it on your own there. And then if I switch, you ought to see a cyan-filled circle over here and a red-filled circle over here. Again, over here you had the cyan, which was blue and green. No red was working, and so when we switch, all the reds jump out and say, hey, look at me. Same thing over here, you had all the reds going, and then all of a sudden the blues and the greens get some attention. So it's always the opposite colors. You remember back when we looked at the colors with that. Same thing happens here. And again, just pause it as you need to and advance to the white background to see the afterimages for each of those. This one right here is one of my favorite ones. If you've ever had sherbet, you may or may not have kind of type of ice cream. I think the afterimage of this one looks like sherbet. So give it about 5 to 10 seconds and you flip it. And what's really nice about this one is you can really see a black section come up in here where that white in the center of that diagram, right in here. Because of the contrast of the other colors around it, you're really able to see that black, which is the opposite of white. Right? White is all the light, black is no light. This one's a little more complicated. You may remember Marvin the Martian from Looney Tunes cartoons, if you've seen those. So you stare at this one, right, give that a few seconds and everything. Usually if you stare right around in here, or if you want to see a lot of detail, maybe right around in here as we switch. Ready? Boom. Just kidding, that's the actual inverse of the image. So if you do have any trouble seeing any of these after images along the way, if you just flip the inverse colors on these, you'll see what the after image should look like. So I'll give you a real shot at this now. And then I'll go to the white screen. Again, pause as you need if you need more time. And this one's a little bit harder to see. It doesn't last as long. You might really need to blink to see that one. This one shows up. If you've seen anything about after images, you've probably seen the one of the American flag. You generally want to stare to this star right here, and then again go to the white background, and you should see the normal American flag where the yellow opposite turned to blue and the cyan opposite turned to red, and so on. So those are the after images. So moving on to the electromagnetic spectrum again, after the visible light, beyond the violet part, or greater frequency than the violets, are the ultraviolet, which we listed as UV. This causes sunburns, skin cancer, tan, kills germs. Some interesting images I found with this. Some scorpions, they reflect light in the ultraviolet. They kind of fluoresce, look very different. So you may have ever been in black light, maybe amusement parks, roller skating rinks, things like that, where you have white shoelaces glow and your fingernails look different colors and teeth and so forth. That's what's happening in the ultraviolet, and it's the ultraviolet A range, which is fairly safe. The ultraviolet B and higher is where it gets dangerous and causes cancer by mutating actual cells. Checking for forgery on American bills, and most countries have some variations of this, but you see these different colors under the black light themselves to see that that's a legitimate $100 bill there. Alright, moving on then, we have X-rays. Again, these will penetrate tissues, typically not bones, and this allows you to see inside the human body very often. So you may have had an X-ray made at a dentist or a doctor. And what's interesting about X-rays, they're not made typically this way anymore, but originally they're made with actual films, photographic films, and photographic films have a silver compound on them, and when silver compounds oxidize or exposed to light, they turn black. And so the area where the X-rays are exposing the film is black, but the part where the X-rays don't get through is white, and that's why we have a negative image when we talk about traditional photography. And this device over here is something my dad told me about when he was a kid. You go to the shoe store, and they had this machine in here that allows you to see an X-ray, a live X-ray of your foot to see if the shoes fit. So the extra video that I have to go along with this gives some more details on that if you're interested in that. Last part of the electromagnetic spectrum then are gamma rays. These are the most energetic. They're originally known as cosmic rays because they were discovered coming from outer space beyond the Earth. They're now known to come from nuclear radiation, from reactions and decays that take place there, and these result from the transition of nuclear particles, protons and neutrons, not the electrons that we talked about previously in terms of light production. One of the main uses that we might see this in the medical field is what's called a gamma knife, where you can focus the gamma rays onto a tumor to kill it. It's used for other types of radiation therapy for cancer as well, in different situations. So that's all for the electromagnetic spectrum. That'll do for this, and we'll finish up the light stuff in the next video, talking about rainbows and 3D movies.